Ladies and gentlemen, good afternoon. It's a great honor for me to be here today and give this lecture. I hope you can hear me well. So in the past couple of decades, we have learned that there are literally billions and billions of planets in our own galaxy. For the moment, this is a statistical information. We expect statistically that every star in our own galaxy should host at least a planet. Unfortunately, we don't know yet all these billions of planets, but we're getting there. And in particular, for the moment, what we do know, we have discovered about 4,000 planets orbiting our stars. That's what we call exoplanets. And I think the most revolutionary thing of this particular new subject is not just the number of planets being discovered, is also looking at the parameters that these planets seem to cover. So what you have in this graph here is the planetary radius of some of the planets discovered and the semi-major axis, so the distance between the star and the planet. And here you have the planets in our own solar system. So even just with a first glance, you can see that most of these colorful dots that are representing exoplanets are not really covering the same parameters of the planets in our own solar system. And so this is, of course, a very big surprise. We also look at planets with some orbital configurations of parameters which are very strange. The planets in our own solar system are orbiting in mostly circular orbits. But over there, we have planets with eccentricity that are going up to 0.9, so more similar to comets really than to planets. And so there is all this variety, all this diversity that seems to indicate that the solar system is not really the standard model of planetary system in our own galaxy. And the question is why? Just to give you a few more examples, taken more recently from the literature, you have here an artist's view of the Kepler 90 system. This is the first planetary system being discovered with 8 planets, and actually planet number 8 was discovered thanks to Google. Google uses some of these very clever technique to help finding a new planet in the data of Kepler. But also quite extraordinary was the discovery of 7 planets, rocky type, in between the size of Mars and the size of the Earth, around an ultra-cool dwarf. So we're talking about a star that is really, really small and cool compared to our own sun. And we are finding these 7 planets around that are all rocky. And on top of that, since this star is particularly cold, although they're orbiting quite close to the star, the temperature actually is quite mild around these planets. And so some of them are located in this habitable zone, as we call it. So an area around the star where potentially you can have liquid water. So you can imagine the excitement of many scientists in trying to understand what's going on in some of these planets. Even more recently, it's just really 1 week ago, we have seen the news that the first exomoon has been discovered, and that was really an extremely positive, and I was extremely happy to see that for 2 reasons. First of all, discovering an exomoon is great, but also because the person behind this discovery is David Kipping, and he was my first PhD student here at UCL. Already during his PhD, he was already really obsessed about finding exomoon. He found a new technique, he wrote papers about how to find an exomoon. And back then, although we all thought it was a brilliant idea what he was putting forward, we were also warning him, be careful, maybe there are exomoons, or maybe it's even more difficult than what you think. But I'm glad that David really was sticking to his plan and went to the United States. He's now a professor in Columbia. And the announcement of the exomoon, it really means that it pays off really trying to pursue your own dreams. I'm really happy for him. Also, quite recently, we have learned in particular from the statistic of the Kepler mission. The NASA Kepler mission was launched in 2009. And the Kepler mission was launched to find originally the statistic of Earth-like planets. So how many planets, more or less of the size of the Earth, at the right distance to their own star you can find. But actually, in the end, Kepler did much more than that. And it gave us the very first statistics of planets in our galaxy. Out of the planets that we know today, a good fraction were discovered actually through Kepler, and there are many other planetary candidates that were identified. And so Kepler told us for the first time that actually big planets like Jupiter and Saturn are actually quite rare in our galaxy. Neptune are also quite rare, but when we go to small planets, so planets are in between the mass of the Earth and 10 or masses, then that's where most of the planets seems to be in our own galaxy. So clearly small planets seems to be very trendy in the Milky Way. This, of course, was unexpected, and even more unexpected, the most recent discovery by the team of Fulton and collaborator in the US. What they did was to follow up some of the discovery of Kepler using some Gaia information. Gaia is an European Space Agency mission that is currently flying, doing astrometric measurements of a large number of stars in our galaxy. And they also did some measurements from the ground. And what they came up with was the discovery. Here you have in this graph the size of the planet in units of Earth radii. And so you see this bimodal. So it looks like there seems to be a lot of small planets that are what we call sub-Neptune. So Neptune would be somewhere here in terms of size. And so the planets between Neptune and 1.8 Earth radii seems to be very common. And then there is a little bit of a gap. And then again, we have another peak of planets that are relatively small, more similar to the Earth. And so on top of that, they did some correlation looking at how much these planets are irradiated. And one potential way to explain this bimodal is to look at how much radiation they're getting from the star. The planets that seem to be more radiated seems to be more rare. On the contrary, we're finding a higher density of planets around stars that are colder or in any case at larger distance. And so, of course, we need to understand a little bit more, but clearly this is one of the constraints that we start to get in terms of planet formation and evolution. So where this diversity is coming from? I started by saying that we're not necessarily seeing the same pattern of planets we're seeing in our own solar system, and so where this diversity is coming from? Where qualitatively, we think that this is probably connected to the way planets are forming, and we do know today that planets are forming in circumstellar disks, and so probably, models are suggesting there are a number of ways to form planets, and probably some of this diversity is connecting to the different way of forming planets. And some of these planets we know are forming at a relatively large distance from the star, but then they're migrating, and so there are all sorts of extra complication in where we detect the planets in the final place. So what do we know from observations today? Well, in particular, there was the Herschel space mission and our European Space Agency mission that was launched some years ago. And Herschel was extremely successful in telling us for the first time where and how stars are forming. And in particular, we learned that stars are typically forming in filaments like this. And so these observations from Herschel really gave us the very first constraint on how star can form. But then today we have ALMA. That's another extremely successful observatory on the ground in the Atacama Desert in Chile. And ALMA is delivering incredible observations like this image here. So what you're looking at here is a disk, and the reason you're seeing all this pattern is because you're looking at the dust, and so clearly the dust seems to have a very peculiar type of pattern and structure. And these are the environments where planets are forming. And of course there is a lot of research in trying to understand whether these gaps that you're seeing are formed by a planet that is forming in the meantime. And on top of delivering incredible images like this, ALMA is also giving us the chemistry of these disks. And that is very important because, again, we're seeing a huge complexity in the environments where planets are forming. In a certain sense, if we are now concentrating on the solar system, it's one planetary system, but we can know that very well thanks to a number of observations of in situ type of measurements, but also remote sensing observations. And thanks to that, we know today with great level of detail all the isotopical ratios for not just planets, but also moons and also meteorites, asteroids and small body. And thanks to that, the history of the solar system seems to be a bit more clear. And because of these measurements, for instance, we have very recently understood that Jupiter must have formed very, very early in the history of the solar system, in less than 1 million years, which is extremely fast. And that information actually gave a little bit of a moment of crisis for people that are working in planet formation models, because they realized that their mechanisms to form planets are not efficient enough, and they had to revisit the way a planet can be formed. And so clearly there is a synergy between what we learn from the solar system, what we learn in outer star formation and disks, and exoplanets. But what we're still missing is connecting the dots. And in particular, we still don't have a big statistics of knowledge of exoplanets at the level of detail like we know in the planets in our own solar system. So what we still don't know in a certain sense is what is the chemistry of these exoplanets. And the reason why we want to follow the chemistry is because the chemistry of the planets then can be connected to the chemistry of the disks and the stars, and perhaps we have a way to understand the history and evolution of all these planets. When it comes to chemistry, of course, one potential measurement that you can use to constrain what these exoplanets are made of is the density. For many of these planets, we know the radius and also the mass of the planet, and so of course you can calculate the density. And knowing the density, you have diagram like this one, where you have, these are all different planets with their uncertainties in the measurement of the mass and the radius. And out of this diagram, what scientists are trying to do is to work out, what kind of internal structure, what kind of composition in the interior you can predict in order to match with the density. But as you can imagine, this is extremely crude measurements. It's like trying to define human beings out of their density. Our density is the same of salty water, but it doesn't really tell anything about our nature. And also for planets is really very limited in terms of information. In particular, we know for sure that some of these measurements can have multiple solutions. There are a number of composition that we can think for the interior, especially of the small planets. One way to interpret some of these observations, and some of these planets seem to suggest a density very similar to the one of the Earth, so made of silicate. Some of them are lighter, and so they're more suggestive of icy bodies like the moons of the giant planets. But there are also more exotic composition that one can think of. A very recent paper has provided the equational state for an interior of the planet being made of SiC. So really a more carbon-rich sort of planet. And if that is the case, it means that then you have an extra level of complexity. Or another very recent theory is that some of the super-Earths, when they're forming, they're very hot, and given that they're forming a disk made of hydrogen, they absorb some of this hydrogen in the interior, and the hydrogen gets actually mixed with the rest of the rocks. And so altogether, you end up with a planet with a composition of the interior that is very exotic and very different from the silicate planet we're used to in the solar system. So this is just to give you an overview of how many things exosolar planets are starting to suggest. Okay, another way to go, and perhaps slightly more precise, is to try to think the chemical composition looking at the gaseous envelope of these planets, the atmosphere. But of course, when you're talking about getting the chemical composition of the atmosphere, you might quite rightly suggest that we're looking at planets that are very far away, tens or hundreds of light years away from us. And so at that point, it might be really too difficult or even impossible to measure their chemical composition. But the good news is, the planets in our own solar system, of course, we can measure them more easily because they're closer. But at the same time, they are very cold objects. And so many of the elements like oxygen or carbon or nitrogen are actually not necessarily available in the gaseous form in the atmosphere. They are condensating down in the interior, and so we can't really see them through the atmosphere. And to measure this kind of quantity, you need to send some probes, like the Galileo one in the past, or nowadays there is the mission Juno that is expecting really to measure the amount of water on Jupiter, which we still don't know. But for exoplanets, many of these planets are very warm and hot. And that is great because it means that all these elements are actually carried around by molecules that are in a gaseous form. And because of that, we can think of measuring them using remote sensing sort of information. So how can we measure all these chemical components in the atmosphere? Well, today we have two big classes of techniques in order to measure the composition of exosolar planets. One way to go is actually to use direct imaging, and so what you're seeing here is actually a real planet. This is Beta Pictoris b, and you see a spot in the middle because that is the star that has been maxed out using some technique to rule out the contribution of the star. And so this is actually quite a recent measurement done from the ground. And in principle, not only you can detect a planet in this way, but you can also split the light into wavelengths and then use spectroscopy then to understand what's going on in that planet. Direct imaging was expected to be the only way to get to the composition of an exoplanet atmosphere about 20 years ago. But actually, in the meantime, another technique came out that is extremely successful and perhaps even easier to implement, at least nowadays. And that is using transiting planets. What are transiting planets? So basically, among all the possible orbital configurations that planets can have, if we select planets that at a certain point pass in front of the star or going behind it because their orbit has the right inclination with respect to the observer, then we can use basically the information of where the planet is with respect to the star to separate out the planet from the star without necessarily having to spatially separate them. And so, in particular, when the planet is passing in front of the star, we call it transit, you see a dip in the light that you're measuring from the star. And if you do the same measurements at multiple wavelengths, what you will extract is a spectrum that tells you what are the chemical components of the atmosphere of that planet, because we're looking at the stellar light that is filtered through the gaseous atmosphere of the planet. Or you can wait for the planet to go behind the star, and at that point, when the planet is no longer visible, it's during eclipse, then you have the information of the star alone, and you can use that information then to extract out the contribution of the star, and you're left with the planet. So when you try to explain what we are doing, it seems incredible given that we're talking about very tiny changes in the light of the star, that we can do this to the level of precision to get out an information of the atmosphere. When I'm talking about precision here, for getting to the atmosphere, we need 10 or 100 parts per million the flux of the star, which is indeed really very precise. But actually, this is being done today. And I have just a few examples of what is being done today with both techniques. These are actually a couple of spectra taken with the direct imaging technique recently for another planet, done with the GPI instrument on the Gemini Observatory. And so you can see that out of that spectra, then one can compare model and try to work out what are the molecules being present in the atmosphere of that planet. Planets that are being observed with direct imaging are very different compared to the ones that are transiting. And in part is because for doing direct imaging, you can see from the figure here, it's much easier when the planet is really far away from the star, so a large separation. On the contrary, if you're doing a transit, you really want to have as much as possible a planet that is orbiting close to the star, because then the orbital period is shorter and you have better chances to repeat the measurement over and over. And some of the planets that have been observed so far have an orbital period of less than 1 day or a few days, so it's really very practical in a certain sense to follow the orbit. Okay, so with transiting planet, we started about 10 years ago, actually, here at UCL to try to understand whether we could use observation from space, and in particular the Spitzer Space Telescope that is providing observation in the infrared, and use Spitzer Space Telescope to really understand whether there are some molecules present in some of this atmosphere. And so we started with extremely crude measurements. And if we look at this today, then sometimes we're a bit laughing because we really started with just 3 big bands. But actually, you know, back then there was no information whatsoever about this faraway atmosphere, and these were the very first data that became available telling us something about what was going on. And even 3 very crude bands seemed to indicate that there was an atmosphere, and the way we interpreted that with Jonathan Tennyson was to match with a spectrum of water vapor, and that was a suggestion that some of these atmosphere, in particular the one of big planets like Jupiter orbiting very close to the star, do contain water vapor in the atmosphere. Of course, that was the past. Then, of course, we learned to do better observations, not just with Spitzer, but also with Hubble or from the ground. And today, clearly, things have changed quite a lot. Now, this is the biggest catalog that, for the moment, we have of observations of hot Jupiters, so Jupiter-type planets orbiting very close to the star. Has been done also here at UCL. Angelos Charas has led this effort. And what you're looking at here is this, I'm sorry that is a bit blurred on the screen, but you have basically 30 planets being analyzed being observed with Hubble and being analyzed in a uniform way. And out of these 30 planets, we could understand that for most of those, we could see water vapor in the atmosphere. For some of those, we couldn't see anything because there were some clouds, and so that's why you see some relatively flat information for some of those. And of course, Hubble is not the most ideal instrument really for doing this kind of observation, in part because it has all sorts of systematics. This is a zoom in to one of the spectra. But the other problem is that Hubble is probing the atmosphere between 1.1 and 1.7 microns, so we are in the near infrared. It's a relatively narrow wavelength range, not so many molecules absorbing there, and so we're quite limited in our way to get into the atmosphere. When it comes to super-Earths, so smaller planets, of course, these measurements are more difficult. And today we have a couple of examples for which some measurements have been taken of the atmosphere. One is a super-Earth called GJ1214b. We're talking about 6 Earth masses super-Earth, and let's say warm, so we're talking about a temperature of roughly 400 Kelvin. Unfortunately, Hubble observation seems to deliver a very flat spectrum, and so it's suggesting that there are some clouds, and at least in the wavelength range we are limited to, we can't really work out too much what's going on. Here at UCL we are focused on another super-Earth called 55 Cancri. 55 Cancri is an 8 Earth massive super-Earth that is orbiting around its star in less than 1 day, and so it can reach temperature over 2000 Kelvin. And so it's really a quite exotic world and quite hostile in a certain sense. But despite orbiting very, very close to the star, and we were predicting seeing no atmosphere whatsoever, we did show some modulation coming out of the observation of Hubble that is suggesting that there is an atmosphere around 55 Cancri and seems to be still hydrogen rich. So again, all these objects, we make predictions, but then when we do observe them, they all seem to tell us a completely different story. So clearly we're just really started to understand what's going on in these faraway worlds. As you probably guessed from the data that I'm showing you, the uncertainties in the measurement are still very large. And so we still have a lot of questions. And so that tells us that current instruments are really not optimal for the kind of work that we're trying to do. Most of the time, the signal is very similar to the kind of noise that we're trying to eliminate. And so clearly, we are looking forward to a new generation of instrumentation, and there are a number, in particular, of space missions in the next decades that will deliver new exosolar planets in the first place, in particular in terms of discovery of new planets. Kepler now is retiring. Gaia is still ongoing, and Gaia is supposed to deliver really thousands of new planets. But TESS has been launched in the spring very successfully and is expected to deliver thousands of new exosolar planets with the transiting technique. So we'll have many planets to look at in the future. And Cheops, also from the European Space Agency, will refine some of these measurements. Plato later on, 2026, should deliver even more planets. So we'll have a huge number of planets to select from if we want to try to do our analysis. But if we're interested in the atmosphere, then we need to think about what are the best instruments, and I will touch upon this point in a few slides. So here UCL, in preparation of the arrival of some new instruments more dedicated to the atmosphere, we're really working quite a lot to try to use new techniques like machine learning type or artificial intelligence. My colleague Ingo Wallman just got an ERC to really do this, apply this kind of techniques to exosolar planets, and in collaboration with him and the team of ExoMol, again here at UCL, what we're trying to do is to create an infrastructure to analyze big data an exoplanet. Of course, 30 exosolar planets being analyzed today is not big data, but we're expecting a huge number in the future, and so clearly we need to be prepared for that. And so we are trying to work out how all this technique can be used for data analysis and also interpretation of all this data. And so there is quite a lot of work that is being done in preparation of this future mission. And in particular, what we hope for is that when this dedicated mission will be available, then out of the data, we might be able to use some of these artificial intelligence technique to work out some similarity or some trends in the data and try to use that to classify planets and try to find a taxonomy of planets, something that today, of course, we cannot do. I have just a couple of slides to show you how effective are some of these techniques. You can use them to extract some of the systematics, some of the noise out of the data and really clean the data in a very clever way. But you can also use some of this technique to classify some of the spectra that we're getting out of the exoplanet and try to see whether we should look for specific molecule and how we can understand and interpret what's going on in this faraway atmosphere. But where perhaps we're putting more effort is in trying really to influence what is the future. And so I told you that there will be many missions dedicated to find new planets. But at least until a few years ago, there wasn't really any plan to have a dedicated mission just to measure the chemical composition of exosolar planets, in particular the atmosphere. And because of that, we really started to think what would be the right experiment to do in a short-term future. And we came up with this idea of Ariel. Ariel is a telescope of 1 meter class that will be launched in L2. And Ariel will be able to do spectroscopy from the optical down to the infrared in one shot. So we're talking about between 0.5 down to 7.8 micron. And we proposed this concept to the European Space Agency about a couple of years ago, 3 now probably. We were selected for a phase A study, and then at the end of the phase A in March of this year, we have been selected for launch, which means that Ariel now is no longer a mission COMSOS, is a proper mission, and it will be launched in 2028. So the UK are the PI of this mission because the entire concept started here. But nowadays, Ariel is a very complex not just the mission, but also it includes the contribution of 16 ESA countries. So you see some of the technical contribution to the instrument coming out of many countries in Europe. We also have a participation from NASA that needs to be confirmed, and the UK will deliver the coolers, which are very important for infrared detectors, but also that's where we will do the integration and verification, and it will be done in particular Harwell. So being the new data center in Harwell will be particularly useful, so we can keep track of what's going on with the instrument and really discuss science and instrumentation together. So Ariel will be quite extraordinary because it will deliver for the first time spectroscopic measurement for 1,000 exoplanets. And so we're expecting to take spectra of this precision while the planet is orbiting around the star. And out of that, we can extract what kind of chemistry is going on, what is the temperature of the atmosphere, what kind of clouds, and many other questions. And so we will be able to do that for 1,000 planets. And out of that, we try to use this kind of information about the chemistry to connect that to the formation and evolution of planets in the galaxy. So that's the plan. So in particular, for the bigger planet, we can get to a precision where we can really work out what is the elemental ratios on the planet between, for instance, carbon and oxygen, or nitrogen and other elements. And the reason why we want to get to this level of precision is because we want to connect this information to where the planet has formed in the disk. We believe that these elemental ratios should change depending where the planet has formed, whether very close to the star or very far away. And also we expect a correlation between the metallicity of the star, so the elemental composition of the star, and the one of the planet. And so clearly we want to gather this information for 1,000 planets and star combination and use that to understand all these mechanisms. As I told you, there will be many missions that will just discover planets. Ariel will not discover planets. We will select 1,000 out of all these discovered exosolar planets. And so we want to do that in a good way in order to have a relatively homogeneous sample, and so look at planets around different type of stars, different temperature, different sizes, because we really want to go in a certain sense in a blind way and try to extract a lot of information out of very diverse type of bodies. In the meantime, we're all expecting the launch of a general observatory called the James Webb Space Telescope. The James Webb Space Telescope is a NASA mission with the participation of ESA instrumentation and also Canadian Space Agency instrumentation. And James Webb will be the biggest telescope ever being launched in space. We're talking about a 6.5 meter telescope in space, so a very complex mission indeed. At the moment, the launch has been delayed, and so we're expecting James Webb to be ready in 2021. James Webb will be fantastic really for looking at planets which are very small and in the habitable zone of cold star, like the TRAPPIST one that I was mentioning before. And so many people are speculating that James Webb might be our best chance really of starting to look at potentially habitable planets. Although many people also thought that James Webb could cover to a degree what Ariel can do, if you do the maths properly, then it's not really true. Because even if you assume to use 25% of the time on James Webb for exoplanets, which would be brilliant, but James Webb was launched in the first place, or at least conceived in the first place, to look at very far away galaxies, so we will have to compete also with our scientists to get the time. Even 25% of the time is not really enough to look at a big number of planets. And so if we really want to go for the large statistics, we really need to have a dedicated mission like Ariel. And so that was the science case that was convincing enough for ESA to demonstrate that we really need to have a dedicated instrument in space. From the ground, it is expected also something like the extremely large telescope to be ready around 2025 or so. We're talking about a 40-meter telescope on the ground. Again, this is the next generation of ground-based telescopes. And so clearly with an instrument like the ELT, what you can do is very, very high resolution spectroscopy, but for very narrow wavelength range. And so in a certain sense, space and ground are very complementary, and we hope to be able to use both really to constrain the composition of these planets. Before I wrap up, because I don't want to get too much of your time, there are some drinks after, so I don't want to interfere with that. I just want to show you also some other initiatives that we're having here at UCL, and Raman alluded to that very briefly in this introduction. Although these a NASA mission are actually quite extraordinary, they're all very expensive, very complicated, and because of that, it takes quite some time to build them. Ariel, for instance, is costing 450 million because it takes about 10 years to be built. We are starting now, and it will be launched in 2028, and so that's how much it costs really to have that sort of mission being built. And so we're trying to see whether one could do things in a slightly different way, of course, for science that is less ambitious compared to some of the observatories that ESA and NASA is building. But you know, there is quite a lot going on in Earth observation and telecommunication. There are many small satellites that are being built almost in series now and being launched also very frequently. And so we're trying to see whether that sort of industry, so having smaller platforms, smaller satellites being launched more regularly and therefore costing a little bit less, could be used also for doing science measurements. And so we created this company, Blue Sky Space, to work out whether we can use some of the platform built for Earth observation, be repurposed to do spectroscopy or in general science observations rather than looking down on Earth, and use an innovative business model. Since this kind of satellite are costing much less, then we can perhaps think of using a business model where anybody really, or in general scientists, will buy for the telescope time they use, and one can use that basically to finance the construction of a number of satellites. So whether this business model will work in the end, we shall see. For the moment, we're just very grateful that we have finished the phase A for the Twinkle space mission. Twinkle is our first satellite. It's a 50-centimeter telescope to be launched in a low orbit. And I'm even more pleased that out of the phase A was a technical and scientific phase A, so we have a blueprint of the instrument. Then we were able to raise some capitals from investors, and so now we're entering into phase B. So for the moment we keep going, and actually there is a huge interest from scientists around the world to use twinkle time, in particular for doing solar system observations, so observation of asteroids, comets, moons, but also exosolar planet. That's how in the first place we started to think about this particular satellite to do exoplanet observations, start to do some spectroscopy of the very brightest targets that we can find not very far away from the star. And so clearly Twinkle between exoplanets and planets should be able to deliver fantastic data. And the even more important information is that in principle one can launch it in 3 years. So clearly we're talking about something less ambitious than a NASA or ESA mission, but something that could in principle be launched much more frequently. So let's see if it will work. So far so good. Certainly what is very successful is this educational program connected to Twinkle. That is taking a life of its own. It started as a support program to be able to attract young students of all ages and show them how interesting it can be to work on a new space mission and learn about engineering, spectroscopy, and planets in general. But as I said, it's taking a life of its own, so hopefully at a certain point we'll also have a mission. But in the meantime, there is quite a successful program that is done in collaboration here at UCL. It's called Orbits, and basically some PhD from UCL are working with some school pupils from high school, and together they're publishing some original research paper. And the program is actually extremely successful. A number of papers have been published in that way. And so this is clearly a way to engage relatively young students in school and make sure they understand how intriguing, how interesting it is to do research, real research. Okay, I think my time is over, so let me wrap up the conclusions here. Exoplanets appear to be really everywhere in our galaxy. Billions of planets are being inspected. So clearly it is almost a revolution in planetary science and in astrophysics in general. What we're seeing out of this, of the current sample of planets being discovered is that even very basic and simple parameters like the temperature or the size of the objects all seems to indicate that the planets in our own solar system are not really the standard model of planets in our galaxy. And again, I'm not suggesting that the solar system planets are rare. I'm just saying they are not the only way of forming and evolving planets in the Milky Way. And so we need to understand why. And I hope I have convinced you that a way forward is to try to understand the chemistry of these objects, not really just their basic parameters. And sadly today we do have instruments like Hubble or Spitzer, or also ground-based instrumentation that is helping pioneering the work of observation of the chemistry of this atmosphere. But clearly these are not enough, and so we need to wait for better, more accurate measurements, and so for a next generation of telescope. For sure, big telescope like James Webb or DLT will be very helpful, but if we really want to be able to explore large statistics and really do many repeated measurements, as you should do when you want to understand something so new, then a dedicated mission is the way to go. And I really hope to see Twinkle and of course Ariel flourishing and giving us a lot of new data to work with. Thank you very much.
Thank Giovanna for a fantastic lecture there. I mean, if the idea of characterizing the atmospheres of exoplanets, discovering exomoons, and possibly identifying biosignatures doesn't blow your minds, I don't know what would. So thank you very much for that. Giovanna has very kindly agreed to take a few questions here, and then of course we'll carry on in the drink stage, which I'll mention in a moment, but everyone does have a couple of good questions for Giovanna. Yeah, go ahead, right. Yeah.
Yes, so towards the beginning of your talk, you talked about statistical analysis of the properties of exoplanets. So I was wondering, how you correct for selection bias there? Because I imagine that larger planets are easier to find than smaller ones, so there must be some way, right?
That is absolutely, so the question was about the fact that we should expect some biases in the techniques and the type of objects that we're able to discover, and so whether the statistics that we're showing are taking into account those biases. So it's an excellent question, and in a certain sense what we're finding is going against those biases, because biggest planets of course are easier to be discovered, but actually what we are seeing out of Kepler is the reverse. We are seeing that big planets are actually rare. Jupiter type, Neptune type are quite rare, and on the contrary, all these super Earths, all these small planets seem to be incredibly common. So this is basically going in the opposite direction. So if we have a bias, then in a certain sense it means that there are even more super Earths than what we are finding. And in terms of, you're quite right, when I was showing the statistical basic parameters and trying to overlap with the characteristic of the solar system planets, you're right. For the moment, we don't have yet the full coverage of the parameter space. In particular, planets which are at an intermediate distance are at the moment relatively difficult to find. Because they're falling in between the capabilities of some of the technique. But I was very careful not to say that solar system is rare, but is not the standard model. The fact that we're seeing so many planetary systems in all sorts of configuration tells us that the solar system, again, is not the paradigm. Not necessarily that it's rare. We could say whether it's rare or not in a few years' time when all the missions that I was mentioning before will have complete all their surveys, and at that point we'll have a much more complete, statistically speaking, information of what's going on.
Hey.
Can you tell me, please, how is the division of instrument building, or the division of money for instrument building and observational time likely to be made between exoplanet studies and cosmology studies like gravitational waves, deep field galaxy surveys, and so on?
So the question was how we divide the amount of time available to exoplanets or cosmology and money. Is your question relative to a specific observatory? It could be JWST or in general connected to ESA missions?
Well, it depends which observatory you decide to spend the money on.
Okay, great question. So I will start by telling you what's going on typically for a general observatory like Hubble or like James Webb will be. These are general observatory, and in principle they can serve all the astrophysical community. And so you're competing, typically you're submitting a proposal when there is a call for proposal, and then there is a telescope allocation committee that meets, and the telescope allocation committee will receive all this proposal, rank them in terms of scientific interest or importance, and give time depending, what are the most scientific compelling cases. So that is the rule. Of course, general observatories always try to a degree to make sure that all the communities are served, and so a little bit to cosmology, a little bit to exoplanets, a little bit to asteroids, but in principle the competition is on the type of science, and of course there is a degree of being an opinion because it depends on the telescope allocation committee, but that is changing every year, and so to a degree you're trying to change that a little bit. When it comes to ESA, it's something in a certain sense similar. Also there you have a science advisory body that is trying to rank a mission in terms of feasibility, costs, but also science that you can do. And also that to a degree, of course, you're trying to serve multiple communities. So there isn't a fixed rule, but the expectation is that most of the community at a certain point will get something in terms of time or missions.
Can you look for exoplanets in other galaxies?
Great question. Can you look for exoplanets in our galaxies? In principle, the only techniques that is able to do that is the microlensing technique. I didn't have really time to touch upon microlensing. For microlensing, you're relying on the fact that light is bent by gravity, and so if you're looking at a very far away star, and at a certain point you have a star with a planet around it that are passing in between the observer and the faraway star, you can use this microlensing technique to discover the planet around the transiting star. And in principle, this technique that is already delivering planets around star very close to the galactic bulge, so quite far away from us, in principle you can push the technique to other galaxies. For the moment, we don't have any real discovery in that sense, but in principle, it should be doable.
It's coming. Okay, one last question? Right back.
This might seem a naive question, but given that you've got now a reasonably large data set, I wonder, have you looked at samples of the data with respect to direction to rule out, it's a null hypothesis, to rule out any asymmetries in the direction and therefore biases or selectivities in the parameters?
So just to understand a little bit better your question, you're talking about direction in
with respect to from where we are to the direction we're looking in the galaxy.
Okay, so the question is about whether we expect some changes, some biases, depending on what kind of direction we're looking at in the galaxy. Well, the good news is that all these techniques are sensitive to a different range of parameters. So, for instance, microlensing is very sensitive to stars towards the galactic bulge, so that is the right direction to look at for that technique. For transit, radio velocity, direct imaging, they're all very sensitive to stars. They're all very sensitive to how bright are the stars to a degree. And so you typically look at planets around stars which are relatively close by to us. But there doesn't seem to be too many biases in terms of directions. At the moment, from the ground, we're covering quite well a certain portion of the sky visibility. But mission light tests now are more sensitive, looking towards the polar region. And so for the moment, we don't see too many biases as far as we can tell.
Okay, then we thank Giovanna and Tinetti again, please.
Thank you.